we'll start a new section today. We're almost towards the end, so we have a couple of more sections to go, 14.3 and 14.4. Then we have our last exam, and then we'll be reviewing for the final exam, okay? That's more or less our plan for the end of the semester. So this 14.3 is about motion in space, and the idea is, okay, so let's take a look at the book. Hold on just a sec. All right, so the idea is that this vector parametric equation allows us to describe motion, specifically either in two-dimensional space or in three-dimensional space. And so here's the thing you should keep in mind. So look at the graph on the screen right now, and we already know that a specific vector equation R of t can describe, if you look at the head of the vector, can describe the position of an object moving along. In this case, is this black curve that you see on the screen. The additional piece of information that we can gather from this, the new thing, is that the derivative we saw, we constructed it as the tangent vector, the best approximation of a tangent vector right there at the point where we're evaluating the derivative. And that derivative is not only the tangent vector, it not only specifies the direction in which you are moving, but it also specifies how fast you are going. So if you look at the picture that we have right now, so at time equals 1, we have this red arrow, and it indicates the direction of motion, and it also indicates the relative, how fast the trajectory is, how fast this particle of this object is moving along this black curve, right? So we have another examples right here, right? And the ones that are not there, maybe, I don't know, I kind of think that they would be like these, the ones that I'm drawing, so they have to be tangent, and maybe they could be like the ones that I just drew right there, okay? So that's the first important thing. So the velocity of an object happens to be the derivative. So that's the new topic we're learning today. And we sort of knew already that for linear motion, we knew already for linear motion that the derivative meant the velocity, because it's the rate of change of how the position is changing with respect to time. So it's the same thing here, only we are now doing it as a parametric equation in three-dimensional space, and now we have a vector, okay? So let me show you the definition right here from the book. So right here is what I have just told you, that the velocity is the rate of change of the vector function, r of t, so r prime of t, which is the one that has components x prime, y prime, and z prime. So you take the derivative of the first component, the second component, and the third component. And if you want to talk about speed, see, speed, so notice that velocity is a vector. Velocity is a vector. But if you want to talk about the speed, speed is a number. Speed means it's measured in how fast you're moving per unit of time, without account of the direction. The only thing that matters is how fast, without taking into account the direction. And to figure that out, what we need to do is take a look at how big the magnitude of the velocity. So the magnitude of the velocity, the one that you see now right here, let me put a box around it. The magnitude of the velocity, that is the speed. That's the speed. So if you want to only know how fast it's moving, but you don't care about the direction, we call it speed. and speed is the magnitude of the velocity. So in other words, take the derivative, square it of the x, the derivative of the y component, square it, the derivative of the z component, square it, and then take the square root of that. And then similarly as we did for motion in linear motion in one dimension, the acceleration is the rate of change of the velocity. So how quickly the velocity is changing with respect to time. So is the velocity increasing or is the velocity decreasing? That is the acceleration. And for that, what it means is also the second derivative of the original vector function. So that's the one we have further below right here. Switch to the mouse, and then we'll put it right here in center. So let me again put a little box around it. This one over here. So the acceleration is the derivative of the velocity or the second derivative of the position function. And all of this is summarized on this one over here, and it will be clearer when we see some examples. You'll see in a moment. But before we see some examples, let me just summarize it right here. Right here is the overall summary of what we had just said. So we have a vector function that describes the position of an object in three-dimensional space with components x, y, and z. And then the velocity is given by the derivative of that vector, so with components x prime, y prime, z prime. The speed is just a number, it's not a vector, and that's how big that velocity vector is, which means take the magnitude of the vector that you see right here on top, which is x prime square plus y prime square plus z prime square. And then the acceleration is simply the derivative of the velocity. All right? So let's take a look at an example. And first, you'll see how what kind of differences we have with respect to, I see, I have a question here from Michael. Is acceleration a vector as well? The answer is yes. So the acceleration will be another vector, and you'll see it in, we'll see an example in just a moment. It says, consider the two-dimensional motion. So this one will be a little bit easier because it will only be in 2 dimensions. Given by the position vector, r of t is x and y, and x is 3 cosine t, y is 3 sine of t, where t ranges between 0 and 2 pi. And first it says, sketch the trajectory of the object, then find the velocity and speed of the object. Next, find the acceleration of the object, and then sketch the position, the velocity, and acceleration for the values of 0, pi over 2, pi, and 3 pi over 2. All right, so let's go to the page and work it out by hand, and then I'll show you some animations that will hopefully illustrate this point in a much better way. So let's go to the page. So first, here is our r of t. So it's the x component is 3 cosine t, y component 3 sine of t. And remember, we already learned about these types of equations, right? If you remember, you should already know that this will describe a circle of radius 3 centered at the origin, right? So we should already have a very nice idea of how this will look like. So this is 3 and 3. This should describe a circle. So this green one over here. It's this circle over here. Like this. Okay, now what we don't quite know is how, if it is like I just drew it, right? How fast is it drawn? Where is the velocity? Was it drawn like I did in this positive direction or in the opposite way? All of that, right? So for that, we can figure out what is the velocity. So like we said, the velocity is the derivative of this one. And this is kind of easy, right? The derivative of cosine is negative sine. The derivative of sine is cosine. And the acceleration, if we wanted to, that's the second derivative. So that's the derivative of the velocity. Which happens to be the second derivative of the position, the original function vector. So now we take the derivative of this one over here, right? So it was going to be the derivative of sine, which is cosine. And then the derivative of 3 cosine, which is negative 3 sine, right? Notice how this one we can visualize rather easily because the acceleration happened to be the negative of the original one. So that's super easy now to sketch by accident in a certain, well, we'll later see that this is not an accident. This is something that has to do with the fact that this motion happens on a circle. Later on, we'll see that it also happens on a sphere. But here's the thing. So if we wanted to draw it, then the original function one will be this one, right? So for an arbitrary t, this would be r of t, the vector r of t. Now the derivative one, we usually put it both the derivative and the acceleration. You put the tail right at the point. So the velocity one is negative 3 sine t, 3 cosine t, right? And look how when if we do the dot product of these two, right? If we multiply these two and add these two, we would get sine, cosine, and negative 9, and over here sine, cosine, and positive 9. They could cancel out. So their dot product is 0, right? And so that's an easy way to see that the derivative function is actually perpendicular and it points in this direction, right? I'll show you in a moment later on an even better one. So this is the velocity one, this is v of t. And if you wanted the acceleration, you look, it's exactly the same as the original one, but it points in the opposite direction because it has negative 3, negative 3. And if we put the tail right here, then it would be a vector like this when it points the same magnitude, but points in the opposite direction. So that would be the acceleration, all right? So we've done the 3 parts of a problem actually, and I mean you can do it at pi over 2 and pi and 0 and 3 pi over 2, and it would be even easier, right? You just plug those particular numbers. But instead, what I want to do is I want to show you on Mathematica, I prepared precisely this one, and we can see what happens as we move along. So here is the one we just described. You can see it over here. Let me show to you. Where is it? Right here. And I'm going to draw a, oops. Hold on a second. The chat area is bothering me. Okay, so right here, you can see the 2 functions. So we have 3 cosine t and 3 sine t, and I'm gonna go from 0 to 2 pi, just like the graph we had, all right? So let me clear that. So I'm gonna now move to the other area, and so here. All right, so this is how it will happen as time starts growing. So the red arrow that you see is the velocity, and it always points in the direction in which the particle is moving. This is sort of like how you know where the object is moving. Okay, it points in this direction. All right, and then after 2 pi, and I actually continued it. Well, it just goes on top of the same thing again, right? So it goes over the same circle. So let me just see if I can have it just move along a little bit so you can see. Let's just slow it down. Right? Okay. So this is how it moves. This is exactly what's happening. So this object is moving like you see on the screen, and maybe a little bit faster. And that's the velocity. So I'm going to show you in a moment one with the acceleration. But before that, I wanted to show you what would happen if we change it a little bit, right? So you get an idea of how this is affected and how these vector functions actually help out to describe not only like something static, you know, like the shape. The shape is just a circle, but more importantly is how fast we went over that circle, right? And in this case, look at this vector. It's always the same length, right? You can tell that the speed is constant because the magnitude of that vector is always the same, right? If you take a look at how big that vector is, which we could do in a moment. So, I mean, we didn't do that actually. That's the speed. We didn't calculate the speed. So we're gonna come back to the page and do that in a moment. But once we calculated it, you will see that it is just like it looks over there. So it appears to be the same length all the time. Okay. So let's go to the next I prepare for you. So look at this next one and look at the difference. So what I'm doing now is I wrote, look at my definitions now. So it's still 3 times cosine and 3 times sine for the x and the y. But now I put t squared, right? So now it's 3 cosine t squared, 3 sine t squared, right? And I'm going to show it to you in just a moment. Now, we can tell already that this is going to describe a circle as well, because what happens when you do the first one, the f squared plus the g squared, you're going to get cosine squared plus sine squared. And that's going to be 1 multiplied by the 3 squared. So it was going to be 9. Yeah, so it will be a circle of radius 3. So it describes a circle. There's no mystery there. The difference is going to be on how that circle is traversed. How is the journey of this object moving on top of that circle? All right, so let me show it to you. See if we go down here, right? And you'll notice how this time, look at the velocity vector, how tiny it is at the beginning, right? Super tiny. In fact, it starts at 0. The vector at the initially is just 0. And then as we go along, look what's happening. That velocity vector is getting bigger and bigger and bigger, right? So yes, we are traveling on the circle, but see, we already finished the lap, the one turn around, and we're not yet at 2 pi, right? We're like 1/3 of the way from 2 pi. If we continue, keeps going around, and you don't even see the vector anymore. We will need to zoom out. Let me zoom out so you see how big the velocity vector is. All right, so let's go back to the beginning. See, the velocity vector starts at almost nothing. And then as it starts growing, look how big the velocity vector becomes. Bigger and bigger. And as we go more around, it's actually going faster and faster, right? Now I'm gonna let it go now. Let me just slow it down a bit so you could see. Okay, so it's moving considerably faster than the previous one, right? That's the takeout that we should have from these two. So we're describing the same curve, but this one has a velocity vector which is way bigger and it's increasing. This velocity vector is getting larger and larger and larger, whereas the previous one, it was always kept the same. Okay, so to drive the point home, let's actually have them side by side. So right in this next one, I put them side by side, and I move one of them a little bit to the right. So we don't want the two graphs overlapping. So I put the first one 3 units, or is it 9 units to the right? Okay. So here's the two of them. I think we need to look even further away, even further, I think. Yeah. Okay, so here they are side by side. Okay. The one in the left side is the second one we saw, the one that has t squared. The one on the farther right is the original one. Okay. And now you can hear them side by you can see them side by side. Think of them as like a competition between two graphs, right? And you can see what's going on. So right here at the beginning, the one on the right is winning, right? Because look, the one on the right already starts with a velocity vector of length. Well, it's going to be length 3, you'll see in a moment when we calculate it. So the speed over here is 3 all the time, whereas the speed over here will change. It will become larger. So the one on the right starts with speed 3, so at the beginning it's ahead. But then the other one gets larger and larger speed, and it starts overcoming the first, right? And and very quickly, before the 1/4 of a turn, it's already, the blue one is already winning, and the orange is lagging behind. Look over here, it's already completed half a turn, and over here already completed 1 turn, and this orange one is not even done with the first half, right? And we keep going. And well, the orange one has no chance whatsoever because it's maintaining constant speed, whereas the blue one is increasing its speed, right? Okay, let me have it run from the beginning. Here we go. All right, so that's how it looks, both at the same time. So like I said, both of them are describing a circle, but look at the one on the right, how it goes at the same speed, whereas the one on the left is increasing its speed all the time. And don't mind that it seems like it's getting fatter over here. That's only a thing of Mathematica. It's trying to recalculate everything before it can display it, and it makes it look like this. But if we slow it down, you will see that it's not happening at all. So when we go several laps, it does not go on top of the previous values, right? It just continues on like that. Okay. All right. So let's calculate the speed for these two that we saw, so you can see what's going on here. So let me go back to the page, and we didn't do the speed here. So let's figure out the speed. So what is the speed? Well, the speed is the magnitude of the velocity, and that's the square root of, this is the velocity, -3 sine t squared plus 3 cosine t squared, the square root of that. And that's 9 sine squared plus cosine squared, which we know this is 1, so this is the square root of 9. So the speed is 3. So for this first example, our speed is 3 all the time. If you wanted to do the second one that I was showing you, let me call it R1, the one that was 3 cosine t squared, 3 sine t squared. When we do the velocity, call it V1. Now we need to use the product rule here, right? The quotient rule, the chain rule. So it's 3, then the derivative of cosine is negative sine, but then times the derivative of t squared, which is 2t. Similarly here, it will be 3 cosine t squared times 2t. So this ends up being -6t sine of t squared, 6t cosine of t squared. And let me write it like this so you get to appreciate. So this is t times 2t times negative 3 sine t squared, 3 cosine t squared. And I'm writing it like this because this is a unit vector. This one is a unit vector, this one is not. So if we calculate the speed, you'll see here that the speed increases, right? Because this is a unit vector and we're multiplying it by 2t at every time. So let's calculate the speed in this case. See, the speed in this case would be the magnitude of this vector, which would be 36 t squared sine square of t squared plus 36 t squared cosine square of t squared. If you factor the 36 t squared is sine squared t squared plus cosine squared t squared. That's 1. So this becomes 36t squared, which is 6t. So in this one, in the second one we showed, the speed increases all the time, right? The speed is becoming more and more and more and more. And that's why we go over the circle faster and faster and faster and faster. Okay? Is that clear? Okay, and I think I have one more to show you where we also look at the acceleration. Let's see. I have it right here. Yes, so this is back to the original one, and this time you will also see the acceleration. So this time the red one is the velocity and the blue one is the acceleration. And you can see how the blue one always points towards the center, which sort of makes sense because we're moving on a circle, right? It's like right now us on planet Earth, we're always drawn towards the center of the Earth, right? That's what keeps us from floating into space. That there is a force that is keeping us, pushing us down towards the center of the Earth. So we have a constant acceleration pointing towards the center of the Earth, right? So every time we move on the surface, there will be a component of our acceleration that is going in the down direction. And we'll talk more about that later on when we do some problems that deal with more or less real life applications. Okay, so questions so far? Okay, so let's move it along and let's talk about the next one over here. So we have an example. So we already talked about a trajectory that can be described by two different, so the different vector functions can go over the same trajectory, but travel it at different speeds. So let's talk about now about motion of things where we are on a circle or on a sphere, right, in three-dimensional space. And we'll look at some examples in three-dimensional space for the first time as well. So let me take it back to the book and we'll go to page 886. Okay, and this result is the one that we want to talk about. It says motion with constant absolute value of r. And it says, if you have an r that describes a path on which its magnitude is constant, so if the magnitude of the position of the vector that we're talking about is constant, that means it's always on a circle, right? So if the magnitude is constant, then that means it only goes around in a circle, or if you are in three-dimensional space, then it goes around on the surface of a sphere, center at the origin. And what this theorem says is that in that case, look at this, the r dot product with the velocity is 0, which means that the position and the velocity are orthogonal. They are at 90-degree angles all the time. Okay, and so we're going to prove this first, and then we're going to see some examples. Okay, so why is this true? Proof. So why is it that if we know that R is constant, so suppose that the R is constant, some C. Go back to the page now. Okay, so this is our situation. Suppose we have some R where this is constant, right? And let's remind ourselves, how do we get the R, right? Let's recall that the magnitude of the R, so this magnitude is actually this, is the X function square plus the Y function square plus the C function square root of that, right? See? A different way of looking at it is if you square it, that gives the square root, and then I just have X squared plus Y squared plus Z squared, which, and by this I mean like this, right? Which is the same, if you think about it, as the dot product of the vector X, Y, Z with itself. So this one is Z squared, right? So if this one is C, then the R squared is C squared. So that means the dot product with itself is C squared. And dot product with itself means R of T dot R of T is C squared. Okay? All right. Now, let's calculate now the derivative. So let's take this equation and calculate the derivative. So take derivatives. Take derivatives on both sides. And let's see what we get. So we get the derivative with respect to t of the dot product is the derivative with respect to t of some constant, right? Now, the derivative of a constant is just 0, right? We know that already. And over here, we could do it the way we learned yesterday, last class. The last class we saw that there's a product rule for dot product. So following the product rule for dot product, this would be the derivative of the first one, dot product the second one, plus the first dot product, the derivative of the second one, equals 0, right? And now remember that the derivative of the r, that's a velocity. This is v of t. So this is v of t dot r of t plus r of t dot v of t is 0. But the dot product is commutative, right? If you do a vector v dot w is the same as w dot v for the dot product. The cross product, no. For the cross product, if you want to switch it, you pay a negative sign, remember? But for the dot product, we can switch them. So these two are the same. So this is the same as 2 times v of t dot r of t is 0. And if the dot product we can then divide by 2. So that means v of t dot r of t is 0. And that's what we wanted to prove, right? We wanted to prove that these two were orthogonal, that the velocity and the original function are always at 90 degrees. They are at a 90-degree angle. All right? So this is the end of the proof. So now we can go and do an example. Let's go to the book to do the next example. Is right here. It says path on a sphere. Take a look. It says an object moves on a trajectory described by x, y, z is 3 cosine t, 5 sine t, 4 cosine t, where t ranges between 0 and 2 pi. It says, show that the object moves on a sphere and find the radius of the sphere. Find the velocity and speed of the object. And then part C is a different one. It says consider the curve 5 cosine t, 5 sine t, 5 sine 2t, which is the roller coaster curve. That's like the Pringles graph that we did last class or 2 classes ago with different coefficients. So it goes a little bit more up and down. The other one was times 0.4, if you remember. It says, show that this curve does not lie on a sphere. How could it be modified to describe a curve that lies on a sphere of radius 1, centered at the origin? And that's the second part we will do. All right? So, good. So let's start from the beginning. So, example 3. First part is to show that the object moves on a sphere and find the radius of the sphere. Okay, so to do that, what we should do is figure out the magnitude of the original one. And I'm writing it. So that's 3 cosine t, 5 sine t, 4 cosine t. And we want to find out its magnitude. The magnitude of this one. So let's do it. What is the magnitude? This will be the square root of this number square. Remember, we're doing the magnitude of just the original vector function, not the derivative. We're not doing the derivative or anything here. Just the original one. That, right? Now let's see. This is 9 cosine square plus 25 sine square plus 16 cosine square. And we're just so lucky that 16 and 9 is 25, right? So this becomes a 25 that I can factor, and then it's sine squared t plus cosine squared t, and this is 1. So this is the square root of 25, which is 5. So that's it. That shows that this is on a sphere, and the radius of the sphere is 5. So the pad moves on a sphere of radius 5. All right? Let me show to you. I did an animation of that one. It's my next one here. You can see right here my definitions. Just exactly like the ones we were doing. So the x function is 3 cosine t, the y 5 sine t, and the z 4 cosine t. Okay? And then here it is. Okay, so these are the axes as we've seen before when we do 3-dimensional ones. And there's the graph. And you see the red one is the velocity, right? Now let me move it because we don't quite see anything from that side, but from this side it'll be better. Here it is. You can tell. Maybe right here, look even better. Right, that's how it's drawn from when it begins to where it ends. And then if you keep it going, it just goes on top of it again, right? Now, how can we tell it goes on top of a sphere from this graph? Well, it's not clear, right? Because it looks like a circle, but we're not quite sure, right? Like a slanted circle, right? A slanted circle in free space. And we can't really tell, except I can actually, so here's the same one, but this time I'm also drawing the sphere. So here's the sphere. That yellow one that you see on the screen, that's our sphere of radius 5. And I made it a little bit transparent so we can see what's going on. Otherwise, we don't see anything. And I don't know why it's, okay. That's maybe good. Okay, now let's see what when I go around, it goes like this. And as you can tell, it's always on the surface of the sphere. And we knew that already because we calculated its magnitude. The magnitude of the vector r was 5 all the time. So we knew already that this curve lay on top of the sphere. And from the looks of it, it seems like it's not only, it seems to be a big circle on the sphere, right? We look at it from here, you see that it is, you know, it seems to be like one of the big circles on the sphere. All right. Okay, so that was the first and the second. We didn't find the velocity, so let's find the velocity of this object. Let's go back to the page. What is the velocity? Find the velocity and speed of the object. So let's find the velocity. Velocity is the derivative of the r, and that will be the derivative of 3 cosine t, that's negative 3 sine t, the derivative of 5 sine t, that's 5 cosine t, and the derivative of 4 cosine t, that's negative 4 sine t. So that's it. This is the velocity. And if we want the speed, we need to find the magnitude of the velocity. And that will be the magnitude of the square of this one. So it will be negative 3 sine t quantity square plus 5 cosine t quantity square minus 4 sine t quantity square. This is the square root of 9 sine square plus 25 cosine square plus 16 sine square. And then 16 and 9 is 25. Again, we sort of were lucky that way. So this is sine square plus cosine square, which again is 1. So this is the square root of 25, which is 5. So constant speed. And we sort of saw it on the animation I just showed you. So as the graph was going around, the magnitude, how big the red vector was, seemed to stay the same, right? So this one also appears to have constant speed, okay? All right, so now let's go to part C. Part C on the problem. And it says now it's a different graph, like the roller coaster graph that we saw before with different coefficients. And it says show that it does not lie on a sphere, right? So one way we can do it is we can check that the dot product of the velocity with the position is not 0. If it's not 0, then it doesn't lie on a sphere. And then we can show it, all right? So I'll start by showing it to you. And then it says, how can we modify it so that it lies on a sphere of radius 1, center at the origin? So let me first show it to you. So it will be this one right here, I believe. Yeah. And here it is. Like another version of that Pringles graph, because it's actually, it has more bend, right? So it goes up and down twice, up twice. So it looks a bit like the Pringles graph. And I don't know, just from the shape of it, I cannot tell if it does or doesn't lie on a sphere, right? And I can look also at the vector. The red vector seems to be getting a little small over there, then big, then small again, then big, then small again, then big. It seems like it changes magnitude, the velocity vector. So I can't tell just by looking at the graph. I cannot tell if it lies on a sphere or not. So let's check it. So let's go back to the page. So this time our R of t is 5 cosine, 5 sine, and then 5 sine 2t. So let's do the derivative. That's the velocity. And that will be negative 5 sine t, 5 cosine t. And then the derivative of this, which is the 5 is just a constant. The derivative of sine is cosine 2t, times the derivative of 2t, which is 2. That's it. Okay. Now let's check the dot product. What is the velocity dot product? The original vector function. It will be, it's not a vector, it's a dot product. So it's this times that. That's negative 25 sine t cosine t, plus this times that, the y multiplied with each other. That's 25 sine t cosine t, and then plus the multiplication of these last two, which is 5 times 5 times 2, so that's 50 sine 2t cosine 2t. All right, and you can tell that these two cancel, but this one does not. So this is definitely not 0, right? If you pick values that are where sine and cosine are not 0, which most of them are not, then this number will be not 0. And if it's not 0, that means this is not on a sphere, right? So because it's not 0, because this is not equal to 0 for all t, it follows that V is not on a sphere. Okay, so the last part says, how can we modify it so that it is on a sphere? And we already know how to do that as well, right? Remember, one way we can do it is we can take the original one and divide by its magnitude. If we divide by its magnitude, if you take a vector and you divide by its magnitude, it becomes a unit vector. And all the unit vectors are on a unit sphere. So for part C, to modify R so that it lies on a sphere, we can divide by its magnitude. Then its new magnitude will be 1. And so it will be in the sphere centered at the origin of radius 1. Okay, so that's what we can do. And so here's the R. So we had the R. So let me get the magnitude of R. The magnitude of R will be this. Will be 5 cosine t squared plus 5 sine t squared plus 5 sine 2t squared. The square root of all of that, and that's 25 cosine squared plus 25 sine squared plus 25 sine squared of 2t. And we already know that this cosine squared plus sine squared is 1, so this simplifies as simply 25. So this is just 25 plus 25 sine squared of 2t. So we can divide everything by that. So the new function we can do is we can do R of t divided by its magnitude. So that would be 5 cosine t divided by this number. 5 sine t divided by that same ugly number, 25 plus 25 sine square of 2t. And last, 5 sine 2t divided by that number again. Right, and if we do this one, it's guaranteed to be on a sphere of radius 1. So I'll show it to you now. So here's the one that I had. I didn't divide by the 25, so let me put it here. So I didn't put the 25, so I made it into a different radius sphere, but I'll do it just like it is here. Okay, so there it is. And now should be a sphere of radius 1. Okay, now it is. Okay, so here's our new curve. So it still goes up and down, but now for sure is in the surface of the sphere, as you can tell. Right? Here's different visualizations of it. As I go around, you can tell that the entire graph is on a sphere, and also more importantly, the vector, the red vector, is always tangent, right? As it goes around. I mean, it grows and it gets small, but let's stop at some point. We are at this point right there. If we look at it, you can see that that red vector is perpendicular to the sphere, right? We turn it around right there. You can see how it's perpendicular to the screen, to the sphere, right? So up, down, and then, see, right now I sort of put it upside down, so that's why. But it's important to look at these things from different points of view to really understand what's going on. So this looks a bit like the sign of a tennis ball, right? You ever seen a tennis ball? It's made of 2 pieces, and that more or less looks like the design. It's not exactly the same. It's actually a different one, but it looks a bit like the design of a tennis ball. Okay, questions? All right, so to finish it off, we're going to do one more problem, and this will involve now acceleration in terms of the acceleration due gravity. All right, so I'm not gonna do it in all its generality like it's done in the book. So we'll just do the example from scratch. So we don't need to have all the physics justifications. We'll only understand that when we are on the real world, we always have an acceleration due gravity that is about 32 feet per second square if you're using feet, or 9.8 meters per second square if you're using meters. All right, so let's work on this example. Example 4, it says a baseball is hit from 3 feet above home plate with an initial velocity in feet per seconds of, and there's a v of 0. V of 0 is 80. Neglect all forces other than gravity, so no wind resistance, so we only have gravity. And then first question, find the position and acceleration. And velocity. Find the position and velocity between the time it is hit and the time it hits the ground. And part B, show that the trajectory is a segment of parabola. So we'll take a look at that later on. Okay, so and the initial position is 3 feet above home plate. All right, so let me make a little diagram right here. Okay, so there's home plate and 3 feet above, and we're hitting it with a velocity, initial velocity of 80, right? So we're hitting this, where this is, and obviously this is not the same scale, because that would be a super gigantic vector. It wouldn't fit on my book. But this is 80 and this is 80. So we're 80 in that direction, 80 in that direction, and then boom, right? The ball is gonna describe some path here, like that, right? And it's our goal to figure it out. And the only clue we have here is the acceleration. So we always have the acceleration due gravity towards the vertical direction. So for all times, the acceleration is going to be nothing in the x, but on the y, it's negative 32 because, so the acceleration is like this, because on Earth, acceleration due gravity is negative 32 feet per second square. So that's our only clue. And we need to find out the velocity and the position of the object. And all we need to do is remember what we were doing last class as well. So we know the acceleration is the derivative of the velocity. So we know A of t is v prime of t. So how do we get v from A? Well, what is the opposite of taking the derivative? We take antiderivatives, right? We integrate. So then to get v, we integrate. To get the velocity, we integrate the acceleration. So we need to integrate 0 and negative 32. That's an easy integral, right? So it's the integral of 0. That's just a nothing, right? A constant. And the integral of negative 32, that's negative 32t plus another constant. Okay, so that's our velocity. Now to figure out the constants, we can use the original velocity. So remember at the top of our page, we had that at 0 at the beginning, we hit the ball with 80 and 80, right? So 80, 80 is v of 0. And so v of 0 is c1 minus 32 times 0 plus c2. So this will be c1 comma c2. So if this vector is 80, 80, that means c1 is 80 and c2 is 80. Fantastic. So we already halfway there, right? We already know the position, the velocity, I mean. The velocity is 80 minus 32t plus 80. Now let's find out the original function, because we know that the velocity is the derivative of the original vector function. So to get the original vector function, to get r of t, we need to integrate the velocity. So we integrate this with respect to time, and that's the integral of 80. That's 80t plus c3, and the integral of this, which is negative 16t squared plus 80t plus c4. And we're almost done. We only need to figure out c3 and c4. And to do that, we use the initial position of the object. Now, we didn't write it, but we had a diagram. Let's go over here. So the ball was hit, and at the beginning, it was 3 feet above home plate. And we're thinking this is the 0 position. So we're thinking the origin is right here, right? So, I mean, this depends on where you place the origin, but we're placing the origin right here. So these are the coordinate axes for us. So then that means that the original position, R of 0, is 0, 3, right? So no x, and y is 3 units. Okay, so we'll use that one right here at the very end. So 0, 3 is R of 0. And that's the same as when we plug 0 here. So it's 80 times 0 plus C3, comma, negative 16 times 0 squared plus 80 times 0 plus C4. So 0, 0, everything here is C3 and C4. It's the only thing that survives. So that means C3 is 0 and C4 is 3. And here's our answer. For our final answer is 80t, comma, plus 0, negative 16t squared plus 80t plus 3. That's the vector function that describes the ball as we hit it. All right? And there are more parts to this question, so we can show the rest. So the other questions in the book are, how far does the ball travel? What is the maximum height of the ball? And does the ball clear a 20-foot fence that is 380 feet from home plate? So is it a home run? So we'll pick it up next class and answer all of these questions before starting our last section of the year, actually. All right. So I'll stop soon. Are there any questions before I sign out? All right. Sorry for taking a couple of minutes extra, and we'll continue tomorrow. Stay safe.